Hi guys, and welcome to this video, the second part of the exercise that we missed. It's about covariant Lorentz force and how does non-relativistic limit look like. So this is the Lorentz force. Okay, so what do we have here? We have the energy momentum or the force momentum. We have the proper time. We have the electric charge. We have the force velocity, which is given in this lower and upper index component here, and we have electromagnetic field strength tensor, which contains, it's a one object which contains electric and magnetic field. I have set c to 1, which is a very crude way of saying that I have absorbed the speed of light into neighboring objects that appear in my equations. That's why it doesn't appear. It will not appear. Okay, so first thing is first, let's take the space part, right? Okay, the space part is pi, which is the relativistic momentum, and now we're going to use the fact that d tau is dt over gamma. So this is coming from the time dilation. Why? Because we want to go to a particular reference frame and then use the non-relativistic limit. So we also have to keep in mind that, so this is d over dt, right? So we also have to keep in mind that pi is a relativistic momentum, which is gamma mvi. So you can write this as gamma and then small p, which is the momentum that we need. So the time derivative of this momentum is what we need. So this is a very important remark. Some of you have done this in such a way that have forgotten about this gamma. So pi capital is equal to pi small only in the non-relativistic limit. So we have this thing. On the other side, what do we have? We have q, and then we have this f, and f is the first index is I, and then we have all four indices, all four components, f, I, j, u, j, uj. Okay, so u naught and uj are components of the covariant components of velocity. You can read them off from here, and you get gamma q. And then you have fi0, so there is a minus here from u0 component, and there is also going to be a minus when I use the definition of the electric field in terms of f. And on the other hand, we have epsilon ijk, uj, actually vj, bk. And this thing is just a cross product between v and b in exactly this order, because j and j, k and k follow that order, ith component. Okay, so now we compare, we want to write this one and this one together. You can see that you can already cancel this gamma. And now let's take a look at this component inside. There are two ways what you can do. You can just first expand gamma, d over dt. So now you apply non-relativistic limit, expand gamma to the first order. This is just going to be 1 plus v squared over 2 q, and then e plus v cross b, and then ith component. Okay, so here you see that this term will catch another v, and it will be already third order, so you can neglect it for small velocities. So these velocities are dimensionless, but if you would recover c, then you would actually demand v over c much less than 1. So right now in these units, or in units in which v has been reformulated, so v over c has been substituted by v, then these letters are both dimensionless, and you can just simply say this. This is what we are doing here, and you will get that we recover the three-dimensional force. So this is now fi. Only here, only now this we can say that this is three-dimensional, or you can say Newtonian force, actually better, non-relativistic force, and this is it. Okay, mv is just momentum, non-relativistic momentum, small pi. Yeah, there is another way of doing it. Before you do this approximation here, before you do this, you can simply act with this derivative, and it would act on gamma. right? Because gamma will depend on time. And then you will have another term, and you can play around with that, but it's not necessary. That other term has the meaning of energy radiated, because when you accelerate, you radiate energy, or if you actually decelerate, you radiate energy. And when you accelerate, you gain energy from this electric field or something like that. So that's the space part. The time part, the zeroth component, is dp0 over d tau, which is again the same thing, d over dt. Now I'll change what is p0. P0 is gamma m, or gamma mc if you restore the units. On the other hand, we have q, and what do we have? We have f0i, because f00 is gone, vi. Well, we have ui, which is, well, vi and then gamma. Okay, so this is electric field, so we have gamma q, electric field, no minuses involved, and contracted with vi, which is just simply e dot v. Okay, and if you remember from the lecture, we talked about the four-dimensional force, and we talked about the zeroth component. So this is basically repeating that, because you can read it off either from here, or you can read it off from here. You can read off the meaning of this component. So what is going to be? First, these gammas are going to cancel here. And again, you have the same thing. You can either do the derivative and then demand that the other terms are zeros. You will get something like v dot a times v, and you will demand this to be neglected when you go to non-relativistic limit, because it's the second order in velocity. Okay, but we can do it in the same way like before. So this is just approximately 1 plus v squared over 2, and you can see already here that you have the rest energy and the kinetic energy of this particle. This is equal to q e times v. Okay, so from this side we have that this is del over del t if mass is constant. It doesn't have to be constant. So if mass is constant, then you have mv squared over 2 under the derivative. And the other side is just, let's see what's the other side. So what is q times e? Q times e is just force. It's the Newtonian force, which is which this particle feels from the electric field. So this basically turns out to be F dot V. So this is the very same thing that we had before in the class where we introduced the force. So if this is energy, let's say T is the kinetic energy, the change in time of this energy is proportional to Q E dot V, which is just this force times V, and this is nothing else than power, right? So watts are joules per second or Newton meters per second, and you can also read that from here. This is Newton, V is meters per second. So now I restore the units. So this is just Newton meter per second, and this is just the same as joule per second, right? So this is power, right? So not everything fits. This is really nice. Independently of this being non-relativistic limit, this conclusion is the same in the full four-dimensional case. The point here is that this kinetic energy is changed only by the electric field. That's very interesting. And so the magnetic field just curves the line, the trajectory of the particle, but it doesn't change the energy. And that's I find that very nice and interesting, right? So this is energy per time, it's power, and that's it, right? So we're done, and see you around.